I'm Marek. This is my co-founder Jerguš, and today we are going to tell you something more about TopK, which is like basically enabling better performance and relevance of search results at lower scale and cost. So, who are we? I'm Marek. On a high level, co-founder, CEO of TopK. Before TopK, I was at Pinecone, which some of you may know of. Did like tech leading there, designed their serverless architecture. For that, I was at Shopify, worked on fraud detection, financial forecasting. At CTU Prague, I did like applied game theory and like generative methods to computer security, basically. And random fact about me, I can deadlift 300 pounds and more. How about Jerguš?
Hi. So same as Marek, previously worked at Pinecone. My focus was mostly platform infrastructure. I ended up owning CI/CD. Before that, I did a bunch of other work, going all the way from front-end development to back-end development, platform distributed systems, and all of that. Did my studies in UK. I was really interested in language design, in compilers. And the random fact about me is I'm 6'6", and I do not play basketball, which people often ask me, but I play squash, so make of that what you will.
Okay, so let's start with the core premise of what we are doing, and that's the fact that vector databases are simply the wrong abstraction. And let me explain why. So the primary reason why like vector databases or databases built around a vector index simply don't work is that distribution of vectors and distribution of metadata are not correlated, right? So on the image on the left, like you can see, you are doing vector search, you partition the space, you build an index, and then all of your nearest points are actually around the red dot, which is like the query, right? But if you apply a filter that's not correlated with the vector distribution, like all of the points that actually satisfy the filter are randomly in the space. And so what ends up happening is that you are actually not using the vector indexing at all because you are scanning all the points. And basically like you spend the effort to build an index that you then don't use at query time pretty much at all, or like you made your queries less efficient. The second fact is building the index sort of assumes that you use certain metric, right? So cosine similarity, Euclidean distance, something like that. And basically imputing the metrics into the index at the indexing time basically prevents you to do custom scoring at query time. And like that's large part of relevance engineering, that's large part of actually getting good results is like being able to do keyword boosting, being able to prioritize more recent documents, being able to do like geo search or nearby results. And all of this is not possible if like all you do is cosine similarity basically. And that's sort of the reason like you're approximating a specific distance and indexing time, which like loses this flexibility. Yes. And so the last point is like, as I mentioned, like you are building the vector index, you are doing all of that, which makes writes very expensive, right? Because adding items or deleting items from the index sort of shifts the data distribution, and that sort of requires you to periodically rebuild the index to maintain performance, maintain recall, and that basically like slows down your indexing throughput. And so what we actually build instead. Basically, we started by building a custom query engine that essentially allows you to do all different kinds of retrieval in a single query on a single data set, right? So that you can do dense and sparse retrieval on vectors, you can do multi-vector retrieval with multiple fields, you can do BM25 with lexical scoring, so like standard elastic stuff. You can do custom scoring, which is super important, right? You can actually like tune relevance for your domain. And finally, you can also do filters efficiently, which is kind of hard with vector databases. You will see that like with us, filters are actually faster and make the results perform better. And finally, like we wrap this query engine in a cloud-native database, right? So the database that sort of separates compute and storage, separates the read path and write path. So sort of a lot of writes into the database doesn't really affect the read performance. And we build a storage format from scratch that's sort of optimized for object storage as being the primary storage. And let's see how that works. So for query latency on vectors, like you are not sacrificing anything pretty much at all, but you still got a lot of flexibility in the performance, right? So sort of unfiltered search is like 25 millisecond P99 on a million scale vector set. And then adding filters to like 10% on 1% of the data actually makes the queries faster, not slower, which is usually the case with vector DBs. Similar for BM25, so we did like a benchmark on MS Marco for conjunctive and disjunctive queries that's like roughly 10 million items. And basically the performance you get at P99 is around 50 milliseconds or lower if you do conjunctive queries. Now off to you, Jerguš, to do the demo.
Cool, thank you. So Yang introduced us as with the proposition we're gonna drastically simplify search. So I'm gonna go through demos to show how we would build a search solution on top of TopK. So TopK as a thing is a collection, is a document-oriented database. So if you want to insert data into TopK, you insert JSON-style documents. In this example, what we're gonna do is we're gonna take an example from medical space. So we're gonna take some notion of medical papers, chunk it up into different paragraphs, and each of those paragraphs we're gonna abstract into TopK. This, what you see on the screen right now, is one example of one chunk of that document. So for each chunk of the document, we're gonna have a title of the entire paper, summary of the paper, then the passage, which is basically the paragraph, the chunk we're looking at the moment. And as well, we're gonna take the summary embedding and the passage embedding. So for this, you would just use your standard embedders, sort of insert the vectors as normal fields on the database. I'm also gonna have like two normal fields, which are published year, which is an integer, and then journal quality, which is gonna be more important later, but for now you can think of it as a float going from 0 to 1. All right, so let's start building the search site. Cool. So to build a basic vector search pipeline, this is all I need to do. So with TopK, I'm gonna start my query with select. I'm gonna say the fields that I'm interested in from each of the passages are the title, are the passage, and now to compute the vector similarity between the field called passage embedding, I'm just gonna call this vector distance function, pass the name of the field that I'm matching against, and then pass my query vector. Now to get the results out, I'm gonna call the TopK operator, which some of you know that's the name of the company, hence the joke. I'm gonna sort all of those results by passage similarity, which is the vector distance between my passage embedding and my query vector, and I'm gonna get top 100 results. Cool, so this gets you a basic vector search. Let's expand on that. To introduce some filtering, what we can do is basically add a filter stage where I'm gonna filter all the papers by the published year. So blending vector search and filters is as easy as adding another line in there. As Marek said before, filtering in TopK doesn't reduce the quality of the results. So instead of overfetching from our vector space and then doing post-filtering, what we do is like we filter the results up front and then apply the vector filter. Cool, let's keep going. All right, so now I want to improve the quality of the search by introducing keyword search. I can do that by using the match function, which is gonna take a word and gonna match that against any of my text fields in my documents using BM25 style keyword search. All right. Now this is a really interesting point where the reason why TopK is different from other databases will allow you to do flexible scoring. So instead of sorting by one of the fields, we allow you to sort by an arbitrary expression. So in this example, I'm taking the passage similarity, which before is just the vector distance between the two, the input vector and my passage embedding. I multiply that by 0.8, and then I'm gonna add I'm gonna add the text score to it, which I can bring into scope by using the BM25 score function. So this example clearly shows how we can combine vector search and keyword search in one query in TopK, and then we have the flexibility to define the actual scoring function. All right. Most vector databases, what they give you is single vector query. So you can build your index by inserting vectors, and then you can search again that index using precisely one vector. Now, it's really useful if you can do multi-vector queries. And in this example, what I'm doing is I'm blending the similarity for each passage with the similarity of my query against the summary of the entire page. And again, using the flexible scoring, I can come up with an expression that sort of expresses the importance of every chunk or every part of that query. Now, on the initial example, on the document itself, I had a field called journal quality. Now, in this example, this is something that you would compute either manually or you would have some expert in-house that would actually grade the document and with TopK and the flexible expressions, what I can do is I can use that value of that field and sort of multiply the entire expression by that. So I can introduce my own weighing into the system. Okay, now we've got our queries, we've got our results, and we want to turn on the re-ranking step. With TopK, as easy as calling the re-rank keyword. Under the hood, we're gonna fetch the results, pass to the re-ranker, and then give the results back to you. And now, as a cherry on top, what I'm gonna do, I'm gonna flick between these two slides so it's really visible. What we can do, instead of requiring you to do the embeddings manually, you can just pass the strings and we can do the embedding for you. And it's in a similar fashion as we do the re-ranking step. We can take individual pieces of the search tag and sort of put it under the hood, allowing you to express one query. All right, that's the demo, and we can focus on what's coming next. So what we showed you right now is really what we started with, which is the storage engine. If I switch to the next slide, we call it the unified retrieval engine, and that's the piece that we built right now. I showed you how you can insert strings, or you can use strings to query your data, and we can automatically, embed that, transfer it to vectors. Same what we can do with re-ranking. We can, take the responsibility of integrating a re-ranker, integrating an embedder on our side, and sort of just give you one unified layer. There are other bits which we plan on instead and sort of build a more vertical solution that you can use just to power your search applications. Cool. And that's the demo. Thank you.